Good morning, everyone. Sorry for the delay. I had a computer crash this morning, so that was awesome. Cranked up Zoom and it just died. I am here. So does anyone have any questions? Remember, we got a test that's coming due Wednesday. I put it out on Friday. The practice test hopefully is all functioning. I had a bunch of students let me know that the test had made itself unavailable the other day, and the practice test had done the same thing. I don't know how this is possible. I'd never set dates on practice tests. I definitely set dates on tests, but I'd done them. I had corrected that when I released them, but somehow they turned back. So now I have to ask every time if it's been messed up again.
I had a question about the test.
Go for it, Randall.
I just took it a little bit before class started for the first time, and it asked me a lot of strange questions about redshifting and changing phases and stuff that didn't seem like it was related to what we're talking.
I don't know how that happened. Okay, so actually I do know how that happened, but I don't know why it happened. Oh my God. Okay, so I will kill that test, and I will make the test due on Sunday instead. Evidently that's one of my astronomy tests. So I doubt that's even physics. I mean, we have a section on redshifts and stuff like that, but I can see an easier way for it to screw up and pull my questions from a astronomy bank than I can for it to pull from a different section of physics. So I'll check, but either way, I'm going to kill that test. I'll record your scores in case you happen to do well. Just if you get 100, I'm not going to take it back from you. But anyways, I will pull that test and get another one because I don't know what's going on there. I'll do that immediately after class. Thanks for that, Randall. I didn't have any idea it was doing that, but oh my God, that's terrible. Anybody else? I assume everybody had the same experience.
I had a question concerning the semi-major axis in the conceptual homework.
Okay.
It says find the semi-major axis. The semi-major axis is equal to the so the major axis is the wider radius on the ellipsis. If you had a long oval,
right?
So a semi-major axis would just be like whatever that long axis is divided by half, right?
That should be the distance called the semi-major axis. The word semi-major axis plays a couple roles. It plays a role as the average distance between the star and the planet. It also plays the role of
the semi-major axis is the average.
Yeah, it also is the average. Yeah, that's another way of wording it. But yeah, half is the normal. It's but what it is half of the perihelion and half of the aphelion distance. In other words, you take the average of those two. Sorry, I said half, but I think you know what I mean.
Well, yeah. So I think I found, I guess my book's over there, but I found somewhere in our notes that the semi-major axis, like a semi-axis, is just half of that like the width, the long ways. Yeah. So I figured that if you had R1 for the short distance and R2 for the long distance, the semi-major axis should just be equal to R2, shouldn't it? Why is it R1 the average R2 as well?
Right. Assuming R1 and R2 are the shortest and longest, or longest and shortest.
Yeah, yeah.
Because there's some times where the R1 and R2 are quite a bit different from the shortest or the longest. So you can't always say it's the average distances. And in fact, if you do a calculus calculation where you calculate the average distance, I seem to recall it might be equal to that times the square root of 2 or something. Meaning it spends a little bit more time farther away than half. But it's been a long time since I did Calc 3. So yeah, with a multiple choice, so they could ask it a lot of different ways where your right answer is right, but that's not one of the choices they gave you. They might have given you a choice that's better or something.
So I guess just henceforth I should use that average formula to find a semi-major axis.
Yeah,
R1 plus R2 over 2.
Yeah, as long as R1 and R2 are the perihelion and aphelion, then yes, that would work.
Okay. It was just kind of confusing because I didn't really find anything indicating that average in the notes that I took anyways.
Yeah, when I drew it, I was trying. You might look in one of the videos. What I did was I drew the whole thing, and I said, well, when the sun is closest to the planet, or when the planet's closest to the sun, this is called perihelion, and that little distance is this. And when the sun's farthest from the planet, then that distance is called aphelion, and from here to here. Now, if you add those two, you get the major axis, and if you divide it by 2, you get the semi-major axis. But you also get the average of those two. So in that sense, it's the average of the planets. Average of those.
If you add, I thought that the major axis was like that total diameter on the widest part of the ellipsis.
It is, but remember that widest axis goes. Let me draw it on a piece of paper. I mean, that'll make it easier for you to conceptualize. So I'm turning the document cam on. Make sure, yes, looks like it's pretty focused. So if you have your elliptical orbit, something like this.
Yeah.
Okay, this is your R1. And this is your R2.
Oh, that's what that is with the foci. Foci?
Yeah. From the position where the sun is to the position where the planet is.
Oh, the center of the ellipse is not the point of. Oh, okay.
Yeah.
That's where I was getting confused. I thought that the center of the point of orbit was dead center of the ellipse.
No, that's part of Kepler's first law is the planets orbit in elliptical orbits with the sun at one foci.
Oh, okay. I missed that part. All right.
Yeah. So yeah, you can see when you add those two, you get the major axis. If you take the and divide that by 2, then of course you get the semi-major axis, of course.
Gotcha. Okay. I missed that part. That's my bad.
No problem. Anybody else? Okay, I'm going to go OCD about this and try to fix this horrible orbit for no reason, but because I can't help myself. Okay, that looks a little better. Anyways, does anyone have any other questions? I've got to fix that test 3, and that probably means I got to fix all of them because I was trying to be super efficient and create your class test and then just copy it over to all the classes. So I have no idea what the hell I've done, but anyways, I will fix this and hopefully have it fixed within a few minutes. Sorry for those of you wasting any time trying to take it. Has anyone taken it more than once? Good, that makes me feel a little better anyways. So the reason why I asked if you had a couple of questions like that, or all the questions like that, because there's a way where I could have given you just one bank. And I could see that mistake a lot easier, where one of the banks that I use for one of the questions repeatedly comes up from an astronomy bank, and then the other ones come from the real stuff. But I can drill down and look at that to see. I was just trying to get a diagnostic from this side. So what I'm going to do now, guys, is I'm going to introduce you to the concept of work, and then we're going to go into another tool for vector analysis, because that comes in really handy in this particular area of work. So what you might know is if you were a small child that ever had to cut grass with a push mower, you probably figured out some physics, whether even though you didn't mean to or you didn't know you did, but you probably figured out some physics. And what it is we're always a little bit too short, at least I was when I first started cutting grass, was a little bit too short to walk comfortably pushing the lawnmower like this. It was like I was always about this angle or something like that. And what you ideally want to do is you want to push like this and then push the lawnmower ahead. But by the end of the mowing of the grass, you were down like this and your arms were pushing perfectly horizontal. And I even at one time reached down and grabbed the crossbar of the handles and was pushing it like that. And you're down and you're leaning all over like this, and you're pushing the lawnmower straight ahead with your arms perfectly horizontal. What that is sort of your body figuring out that the most efficient way really is to make your force parallel to the direction you wish to travel. So you're wanting to push a lawnmower horizontally. If you're tall enough to push downward horizontally, then you can sort of, well, you're sort of making use of the way the lawnmower is designed. and the lawnmower will sort of automatically make that weight not so bad. It still makes it a little worse, honestly, but because of the way it's designed, they put the handle with respect to the wheels in just the right spot where it doesn't cause as much problems. But if you're not tall enough to do that, and I'd argue you have to be like 6'5" to do it properly, then what you end up doing is pushing downward like this, so that the handle comes forward in that little groove that it's got, because it has the ability to go from here to here. The handle comes forward like that and pushes the lawnmower. When it does that, it actually lifts up on the lawnmower a little bit because it's trying to rotate it. And that actually does make it a little harder, but it's still easier than when you're pushing completely up or completely down. Because when you're pushing down on it, it turns out you've learned that you increase the normal force, and therefore you increase the force of gravity. Or excuse me, increase the force of friction. I don't know why I said gravity. So yeah, when you're actually pushing down on it, you're increasing the normal force. The normal force is proportional to the friction, or the friction is proportional to the normal force. So because of that, you end up getting increased friction, and you make it a little harder on yourself. But if you push perfectly horizontally, then what you're doing is pretty much applying, because of torque, you're actually applying a little bit of more normal force in the front and less normal force in the back, but it's still easier for you than increasing the normal force on the back, which is what you do when you're pushing down. So that's a neat instance, and it gives us an idea of how to think about work. When you go to cut a lawn, I think you can make perfect sense out of work by thinking about it this way. You know, your work is to cut a yard, say. Now that's a total job, but if you want to know how much of a job it is, you might say, okay, well, I can do, you know, X number of acres or something like that. Well, the easiest way to translate acres into mowing is you take the width of the blades, say a 42-inch blade lawnmower or 28-inch blade lawnmower, something like that. That's the width of your path. And then you say, well, how many miles did I walk? And then you multiply miles times 28 inches or whatever, convert that to square feet, divide that by 43,560, which is the number of square feet in an acre. And that would tell you how many acres you cut, right? So I think y'all all would agree that the more miles I walk, the more work I did. Does that make sense to everybody? So yeah, work is directly related to distance. Now, if your fat little baby brother wants to sit on top of the lawnmower, and you know that he's going to get burnt, so you're like, yeah, if he wants to be a jerk, I'm going to go ahead and let him get burnt. And so you sit on top of the motor. Now you're pushing a much heavier lawnmower because your little brother's a fat butt. Excuse me. So, anyways, so you let your little brother sit on there. I think you'd also argue that because your brother weighs more, you're having to apply a bigger force. So you'd probably say that force and work are directly related. Would y'all agree with that? Okay, so we've got this nice scenario. I'm going to turn on the document cam again. What we've discovered is that our everyday life definition of work suggests that work, which we're going to use the symbol W for, is proportional to distance, and it's proportional to force. And lo and behold, you'd be exactly right. In other words, that is exactly the two of the factors that work depends on. Now, if we take into account our lawnmower problem, we see that applying a force this way over a distance vector d that way, and if we were to, for instance, put them head to tail, or excuse me, tail to tail, we'd see that that angle theta is the same as this angle theta, right? What we really want, though, is to realize that this component of the force, which I'll call F perp, and this component of the force, which I'll call F parallel, those two forces are both part of the force that you're putting into pushing the mower. But this one right here is not only being wasted because it's not working in making the distance go farther because it's perpendicular to that distance, but it can in fact make the work even worse, as I showed you, because when you're pushing a lawnmower, that's causing the normal force to go from that to that. And therefore, the friction force goes from to. Does that make sense to everyone? So it turns out if you were to make a vector for force and a vector for distance, then work is actually equal to F magnitude D magnitude times the cosine of the angle between them. Let's notice if I take F and multiply it by cosine theta, I get this component. Well, that turns out to be equal to a mathematical thing called the dot product. Of two vectors, okay? So we've already learned about adding vectors, subtracting vectors, and multiplying vectors by scalars. This is one of the two ways you can actually multiply a vector by another vector, okay? There's actually more than two ways, but the ways you normally learn in pre-calculus, say, would only be two ways. In advanced calculus, tensor calculus, differential forms, you'll learn that you can also do an outer product, which is, this is also called an inner product. But you could do something called an outer product that actually makes a big matrix, and it's just a nightmare. But anyways, so for completeness, I'm telling you that other products exist, but in our realm right now, there's two products. There's a dot product, also called an inner product, and then there's a cross product, also called a vector product. We're not learning the cross product or vector product right now, but we are learning the dot product right now. And you can see that another way of talking about this, let's say dot product is, I don't know, let's say dot product is D, defined to be A dot B. So I'm doing a generic expression for a dot product now. It's also called a scalar product, by the way. So I wanted to just say that so you'd see that I didn't put a vector symbol over there, but it's A dot B. And we normally draw the dot kind of prominently, not like an open circle like this one, but just prominently so you can see it. And as you can see, one of the ways of writing this is A times B times the cosine of the angle between them when A and B are tail to tail. And notice there's always two angles between A and B. There's A to B, or there's A to B, right? So that A to B or this A to B shouldn't be ambiguous for you. You always choose the smaller of the two, okay? Now, if you look at this from a geometry standpoint, you could extend this, or you could extend this one, just so you see what it's parallel to. Now, if I imagine a line perpendicular to B, I could do that. But if I imagine the line perpendicular to, say, A, then I could do this. And because I do that, I get a couple different things about the triangle. Perpendicular to B, I can see, oh, okay, well, A evidently has a component that's perpendicular to B, which would be, let's say, let's do it this way. That drawing got messy real quick. Let me draw a bigger one, a better one. Hold on. And I made the links too close to each other, so that was another problem. Okay, so if I draw a line perpendicular to B, I see from that magnitude of A times the cosine of theta is just this. So another way we can write this is the component of A perpendicular to B times B. Now, if I consider another way of writing it, I could extend this vector out there and then draw a line perpendicular to it. And I'd see now that this is the component of B perpendicular to A, right? Because B has this component. Actually, I said perpendicular. Sorry about that. That's twice I've written that now too. It's not perpendicular. It's I don't see where I wrote it anywhere. Maybe I just said it by mistake. It's the component parallel. Sorry about that. Cosine theta, notice that is parallel to B. I don't know why I wrote perpendicular, but I did. So anyways, there's A parallel to B. Similarly, when you take the cosine of theta and multiply it by B, you get this thing. Which is B cosine theta. So you can see this is also equal to B parallel times A. So there's a lot of different ways you can actually figure out what the dot product is. And these are just the geometric ones. There's other ways too, mathematically, that are quite nice. So for instance, let me show you what I mean by that. Let's introduce, or we've already introduced them, but you guys know about the vectors I hat, which is literally one I hat, meaning 1 unit long in the X direction, and then there's J hat, and then there's K hat. Do y'all remember those vectors? Everybody feel pretty comfortable with those to some extent? Remember, they're exactly 1 unit long, not 1 meter, not 1 foot, not 1 inch, not 1 Newton. They're just 1 unit long. And the I points in the positive X direction, the J points in the positive Y direction, and the K points in the positive Z direction. So when I do that, I can say this is my X axis, this is my Y axis, and then out of the page is my Z axis. And what I can do is say, okay, well, this vector right here, exactly 1 unit long, is I hat. And this vector right here, exactly 1 unit long, is J hat. And this vector right here, I've got another student coming in. This vector right here is 1 unit long, pointing in the positive Z direction. That's K hat. Oh, I've written it out of the screen. So everybody now remember those vectors? And remember your formulas that you've learned for your dot product. So we've learned that A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So let's look at some things. What is I hat dot I hat? Anybody?
Should be 2, I think.
Remember multiplication, they're not addition.
Oh, it's multiplying. Okay, so just the 1 then.
Yep, 1 times the cosine of 0, which equals just 1. Okay, and then I bet you can probably guess J hat dot J hat and K hat dot K hat. Y'all, everybody agree, or can everybody see why they're each equal to 1? And again, this is what I mean by unit vectors having unit magnitude, no dimensions to them whatsoever. They're just pure numbers. Now, when we get to the nitty gritty of it, we can do I hat dot J hat. Now that's going to be the magnitude of I, which is 1, times the magnitude of J, which is 1. Now the angle between them is clearly 90, so it's times the cosine of 90 degrees, and you should get 0. And I think you can see just from looking at this, A dot B is equal to B dot A. So J dot I is also equal to 0. How about I dot K? Everybody take a guess before someone says the answer, even in your head. Magnitude, cosine of the angle between them. Okay, anybody know an answer? Zero again. And J dot K is 0 as well. Okay, but of course this also means K dot I is 0, and this also means K dot J is 0. So it turns out that when you do a dot product of these things, there's a fancy symbol they use. They use E to represent the coordinates, and if I is E sub I, so if E sub 1, if you have E sub 1, that's I hat, and if you have E sub J and you have J being 2, that's J hat, and if you have E sub K or E sub I, where I or K is 3, then it's K hat. So this neat little way of remembering it is this, where this number, this delta IJ, is only 1 when it's 1 1 2 2 3 3 or something like that, and it's 0 all the other times. But that's basically the rule of dot products. And the only reason why I'm showing you all this, it should be pretty straightforward for you to figure out, even though it's probably, like right now, it's a little bit of brain overload because you hadn't seen this stuff before. But let me show you the advantage of this. A dot B is equal to A sub X I hat plus A sub Y J hat plus A sub Z K hat, dotted with B sub X I hat plus B sub Y J hat plus B sub Z K hat. We can write all vectors, any vector, as A sub X I hat, A sub Y J hat, A sub Z K hat, and the same thing for B, right? Now, here's my motivation. I've got a dot product here that I could only calculate if I know the angle between them and their magnitudes, right? Or get this, if I knew what the dot product was and I knew their magnitudes, then I could determine the angle between them. So it'd be really nice if we had a way of calculating this that didn't require the angle between them. Does that make sense to everyone? Can you see how that might be advantageous to know what the angle between two vectors are?
Yes, because it like determines the application of the force.
Exactly. Yeah, if you find the angle, say, between a normal vector to a surface and the actual vector force, then you know exactly how much force the surface is going to have to sustain, because it's going to take that surface is going to take that force perpendicular to it. You can also use it to figure out things like, what fraction of the force am I going to be subject to when the wind's blowing at 90 miles per hour horizontally and our roof is a 12-12 pitch, stuff like that. So yeah, it turns out, and in fact, at the microscopic or even nanoscopic scale, when you're talking about atoms and molecules, it turns out when you make atoms and molecules, the little atoms orient themselves in very specific structures called lattices, and it helps to know exactly what the shape of that lattice is, and you can normally figure that out by figuring out the angles between them. So if we had a way of having a vector that points from one atom to another and then one atom to another, then we could take those two vectors, and if we do the dot product, we find out the angle between them, because they're not always rectangular. Okay, So on a physics scale, that's another thing, the physics of the microscopic. But the dot product can tell you stuff like what fraction of the sunlight's going to hit my solar panel, what fraction of the sunlight's going to fade my carpet, what fraction of the sunlight's going to fade my Minion's steering wheel cover, that sort of stuff. It's just an important concept because it always gives you the component parallel to something else. Okay. So if we just treat this like a regular multiplication problem, in other words, saying there's a distributive property, and I'll tell you by default, there is a distributive property. So we do first term times the first term, I get AX, BX, I hat dot I hat. And we're also telling you that the dot product is a linear operator. What that means is when I have AX I hat dotted with BX I hat, then the AX and BX can come way out in front, and then I just have the I hat operating with a dot on the I hat. Okay, that's what makes it a linear operator. Now the first term acting on the second term gives us AX BY I hat dot J hat. And the third one gives me AX BZ I hat dot K hat. And then the second term acting on the first gives me AYBX. In this case, it's I hat dot J hat. Plus the second on the second gives me AYBY J hat dot J hat. And the second on the third gives me AYBZ J hat dot K hat. And then the third on the first gives me AZBX K hat dot I hat. The third on the second gives me AZBY K hat dot J hat. And then the third on the third gives me AZBZ K hat dot K hat. That's the whole reason I took the time to work out all those I hats dot I hats and I hats dot J hats and all that good stuff. What we found is I hat dot I hats 1, J hat dot J hats 1, K hat dot K hats 1, but anything that didn't match gave us 0. So now we can go back and say, well, wait a second, this is 1, 0, 0, 0, 1, 0, 0, 0, 1. So we get a really nice expression. And remember, it's actually the number 1 because the dot product is a scalar product. It gives a scalar back, not a vector. So it's just AX BX plus AYBY plus AZ BZ. So now we have a formula for figuring out a dot product without knowing the angle between them. So let's test and see whether I'm right about that. Let's imagine some vectors we're really familiar with. So I'm going to say, this is my x-axis. This is my y-axis. And remember our special 60, 30, 90 triangle? So what I'm going to say is this is going to be ideally 60 degrees. And because it's a 60, 30, 90 triangle, this is going to be square root of 3. In other words, that's the y component of this vector. So let's call this vector A. The x component of this vector is going to be 1. And then, of course, the magnitude of this vector is going to be 2. Okay. Now what I'll do is I'll say vector B is just 10 I hat. Now I could just dot it with I hat, and that would be beautiful and give me exactly the right answer. But I wanted you to see what happens with that 10, that magnitude of 10 of the vector B. I wanted you to understand where that goes when you do this. So by me writing this vector this way, I've managed to give you the components of A. So A is equal to 1 I hat plus the square root of 3 j hat, and then it has no k component. And then the magnitude, or the vector B, has just the 10 I hat. So let's calculate A dot B. And what I'm going to do is I'm going to calculate A dot B using this, and then I'm going to use that to determine the angle between them. So use to determine theta. Okay, that's the problem we're doing. Even though I know the angle is 60, I'm just doing this to prove to ourselves that this does exactly what I think it does. So A dot B is going to be AX times BX. Well, that's going to be 1 times 0. And then plus AY times BY. Ooh, excuse me. AX BX. Duh. Stupid idiot. That's 10. I said AXBY for some reason, or at least that's what my brain heard. So AXBX is 1 times 10. AYBY would be the square root of 3 times 0. And then 0 times 0. So basically all I get is A dot B is equal to 10. Okay. But I also know that A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. Well, that means 10 is equal to, I can see that the magnitude of A is 2. And I can see that the magnitude of B is 10 times the cosine of theta. So I think you can now see that if I solve for theta, I get cosine theta is equal to 1/2. Notice the 10s cancel out. That means theta equals the cosine inverse of 1/2, which I think you can tell cosine being adjacent over hypotenuse is 1/2. So that's actually 60 degrees. So that's our check to confirm that in fact, this formula does seem to work, at least in this special case. And in fact, it's been proven over and over again. So you've got two major forms of dot products. You can write A dot B in a geometric way, in which case it's A times B times the cosine of the angle between them. Or to compute it, you can sometimes write A, maybe that's where I wrote it wrong, A parallel B equals B parallel A. I don't see where I wrote it, but I remember saying this. Oh, there it is. And I did write parallel. Okay, that's cool. But it's also equal to AXBX plus AYBY plus AZBZ. So that's the big take home. And this, of course, in your book is a formula that's labeled, so it's certainly something you can do. And it comes in super handy for me. Like, how many of you, by typing me in the chat, how many of you actually use the law of cosines very frequently? I got one. Yeah, I got some no's. Yeah, I don't. And the reason I don't is I can never remember what that angle is. Right? It's, B squared is equal to A squared plus C squared cosine something or some crazy crap like that. Well, let me show you how wonderful the dot product and understanding it is, because now I can consistently use the law of cosines very easily. So I'm going to do this in black. I want you to think about this. Let's say vector A is this guy. And let's say vector B is this one. Remember, we've got them tail to tail. So if I want to add them, I have to complete the parallelogram and then go from the common tail to the opposite corner, and that C is equal to A plus B. Okay. Now you could have also just drew it head to tail, and then this would be A and this would be B, and that's fine. It's just this way helps me for what I'm getting ready to do. Okay, because right now you can easily see what the angle is between A and B. The angle is this angle theta right here from our dot product, in other words. Okay, so if I write that C is equal to A plus B, and then I dot product it with itself. So I'll say C dot C is equal to A plus B dotted with, there's a dot there, A plus B. You can see what happens on this side. This is just the magnitude of C times the magnitude of C times the cosine of 0, because C is parallel to itself. So I get C squared. In this case, I get A dot A, which is A squared, just like C dot C was C squared. And then I get A dot B, and then I get B dot A, and then I get B dot B, which is just B squared. And we've already found out, at least in this kind of stuff we're doing, A dot B and B dot A are equal to each other. So I can just call this 2 A dot B. So I'm now going to say C squared is equal to A squared plus B squared plus 2 A dot B. Now it's starting to look like the law of cosines, isn't it? And in fact, the law of cosines can be written in several different ways. Some of them have minuses here, all sorts of cool stuff like that. But now I can write it in a way that I own, and that makes sense to me. It's C squared is equal to A squared plus B squared plus 2AB cosine that theta right there. Right? Now, that tells you exactly which theta we're talking about. If you wanted to use the normal form of the law of cosines, you know, I can Google that, and you'll see there's a minus and all this stuff, and it's because they're using a different angle. Sometimes they'd use this angle right here. Sometimes they use this angle right here. You can get all those equivalent forms, but this is a version of the law of cosines, but it's one that you can immediately understand because you understand the dot product. Does that make sense to you guys? So that was the most enlightening thing I ever discovered about the dot product. And I just, put it together one day myself, just looking at it when I did A plus B and did a dot product of A plus B with itself. I got this, I was like, oh crap, now I can figure out the law of cosines, because I never would take the time to commit to memory where this theta came from or what the actual theta was in the law of cosines, because I couldn't see the derivation of it. It didn't ring as a story to me. I needed a narrative. Well, now I've got a narrative that fits a formula that isn't necessarily the exact same version of the law of cosines that I'm used to using or that I was originally taught, but it is a version of the law of cosines. So it completely works and you can run with it. Any questions on that? All right, so now that we only got like 1 minute left. So what I want to tell you now is this math was strictly so we can use this dot product over and over. But for right now, it's because work is equal to F dot D vector, provided F is a constant along D. If F varies along D, then all bets are off and we end up having to do this. Work is equal to the integral of F dot D, let's call it dx or dr or dl, something like that. Okay. So in other words, if f varies like that along some space x, say, then what you're going to do is you're going to take this little piece, you're going to define the dx vector right there, and you're going to take f with it, take a dot product, and then you're going to do that for each of these little segments and add them all up, and you end up getting the area under the force versus versus distance curve. That's ultimately the formula. It's called a line integral, though we can sort of ignore that aspect of it being a line, the line integral aspect of this integral, but that's what it's going to be. The unit of work, I think you can tell, is 1 Newton times a meter, but that's actually defined to be 1 joule. And 1 joule is about as much energy as required to lift the red delicious apple from the ground to a tabletop, say a dining room or kitchen table. That's about how much energy joule is. And it's spelled Joule. All right, so we've got a pretty good start on what work is. Next time we'll finish this chapter on work. It's actually a really short chapter, and then we can start going into conservation of energy, because once you have work, you can then make the work energy theorem, and then you can also make sense of the conservation of energy, which says the total kinetic energy plus the total potential energy must be a constant unless you put work into the system or steal some work from the system, in which case you got to account for those. So if anybody has any questions, everybody's free to go. If you do have questions, I'll wait around to answer them.
Can you go back to the end? Yeah, the end of the bit on kind of like foiling out the dot product there.
Like that part?
Yeah. So I saw the cancellations and everything. And then I got a little lost after the cancellations, basically, where it came out to ax or a sub x, b sub x plus a sub y, b sub y.
So it turned out only the ones along the diagonal were ones.
Yeah.
Because that's where the I, J, J, and KK is.
Yeah, I got that. I was talking about like right after that part.
Okay, gotcha. So
basically the example.
Gotcha.
Much.
So what I was saying is the reason that it's valuable for us to have another way of calculating A dot B is we see that in this case you need the magnitude of A, the magnitude of B, and those are easy to come by. But the thing that's hard to come by is the angle between two vectors without drawing them perfectly to scale, or even if you do draw them perfectly to scale in 3 dimensions, it's a nightmare to get that angle theta. So this isn't normally, or most of the time I would argue, we do not use this to calculate the dot product. Most of the time we use this. So by having another way of calculating A dot B, I can say this side equals 10, say, and then I can put in the magnitude of A, I can put in the magnitude of B, and then write cosine of theta and use that to determine the angle theta. That was the advantage of having this extra formula. And that was what I was arguing. And I said, okay, so let's do that with this particular problem. And I made up one where I knew the answer was going to be 60 degrees because I took the 39
gotcha.
triangle.
Okay, gotcha. Mm-hmm.
So I did one whose answer I knew just to convince you that it gives you the right answer. So I took the 60, 30, 90, which is 1 root 3, 2, and I dotted it with 10i just so I could let you see what happens to the I, the actual second vector's magnitude is in there in the dot product. So the dot product by itself isn't that useful. You got to do things to it to get, the component of A parallel to B, for instance. That's an actual thing. It's called the projection. But in seeing that, when I went to solve for the angle, the 10s canceled out, so it didn't matter anyways. And I just had to find the cosine of theta equals 1/2, which gave us theta equals 60 degrees.
Gotcha. All right, thank you.
No problem. Anyone else?
I was wondering, do you recommend to study for the midterm? Is the best thing to study is your practice test?
Absolutely. I would say maybe if you can occasionally do one of the previous practice tests, just mix it in there and then, that's the best thing. But yeah, the practice test that I make for the midterm is the best.
Okay, thank you so much.
No problem. Delaney, do you have any questions, madam? All right, I'm thinking that you might have been booted, so have a good day and I will see you next time.